Welcome back, Math 170. We are looking at one last technique of finding volumes of revolutions of solids. This last technique in this section is called volumes by cylindrical shells. And so before we get into that, I just want to quickly review the two methods we learned in 5.2. The first one being disks. So for example, one, bear with me. If you want to try it on your own, you can see what you remember. So I'll let you press pause or just continue to watch and you'll see us model this example one for you. So we're looking at finding the volume of the solid obtained by rotating the region bounded by y equals x cubed, y equals 8, and x equals 0 about the y-axis. So we remember when we were dealing with these, we always wanted to make sure we understood what we were revolving the solid about. So if it says about the y-axis, we're looking at eventually using dy in our calculations. So then when we would try to understand, should we use a disk or a washer? Obviously this example has labeled disks, but to reason this y, we would draw a cross section. And the cross section is always perpendicular to the axis you're revolving the solid about. So you notice if we're looking at the y-axis, this would be the axis in turn. And the solid or the cross section, we will see, okay, it's perpendicular. And so what you want to pay attention to, if you want to draw a cross section, you will see in the next figure, it clearly justifies why we would be using a disk. So we kind of notice, hey, there's no hole in the middle of our solid. So it's kind of a heads up there. So then what you want to notice for yourself is when we are trying to deal with disks, we're always looking at understanding what's the volume of one. So we kind of have a quick formula. If you're looking at the disk, it's like a mini cylinder. So it's always the volume would be pi r square times our thickness, or times h if you were really looking at the cylinder. And then we already kind of know that when we already are revolving about the y-axis, our thickness will be delta y. So at least we can kind of set that up for the meanwhile. So then the goal would be to understand, well, when we do take the volume of the solid, we do have an integral. And you're right, we are looking at it pi r squared times thickness. And in thickness, instead of writing delta y, it's the dy. So then it kind of gives us a justification of what should our y values be doing on the limits of integration. So we'd have to understand, well, do they give us the y values? And in our case, they do. According to what the solid is doing, it looks like the y value is going from 0. And according to the bounds, it's stopping at 8. So then the goal is, if you are trying to understand how to integrate it, you need the r square, or actually just the r part. That's going to have to be rewritten in terms of y in order for you to properly integrate. So then you kind of go back to your picture and you're saying, okay, well, looking at the radius of my disk, thickly highlighted there. And when you try to understand, there's a point value going on. So you can kind of see that as far as the cross section is concerned, I'll kind of draw a little dot in green. That dot is labeled by x, y. Well, in our case, if you're trying to relate it to the ordered pair, I believe that as you draw cross sections along the solid, you might want to note, we can even do this here if you like. Maybe I'll draw one in purple just so that we can see this. Or we can draw another one down here. What you might want to pay attention to is that your R varies along the way. And I'll try to plant that seed in your mind so that we can kind of think about this when we get into shells. So, as you move along the solid, in case of, I guess, if you're towards the lower end of the solid, your R is smaller. And when you get to the higher end of the solid, it looks like your R is getting longer. That's going to help us understand what's happening. If the R is varying, it's not just a constant the whole way through. We have to relate it to the ordered pair. And in our case, it looks like R is a horizontal distance. So this is kind of telling us that our R is equal to the X value of the point on that solid, or I should say cross section. Well, if you want to understand this, you're saying, well, I do know that R will be in terms of X. So we could write it right here. There's no problem. You kind of develop this as you're trying to figure out the volume of one. So yeah, we could say, okay, that's the same thing as X squared. Thickness is still delta Y. But the issue is we can't touch it until X is in terms of Y. So we just have to go with the relationship and understand, well, what was the curve doing? In our sense, the curve was Y equals X cubed. So if we want to look at the Y value, we could kind of look at the ordered pair. XY turns into X and X cubed as Y equals X cubed. So if we're kind of looking at it, oh yeah, I mean, they gave us that particular curve to look at. If R is equal to X and Y is equal to X cubed, we now can write X in terms of Y. So then what we do is we solve for X. That would be taken maybe the cube root of both sides. So we should get X is the same thing as the cube root of Y. Therefore, finally being able to write our curve in terms of our Y's. So now we have, instead of X, we could say cube root of Y. And then now we're in business here. Don't forget, we still have the square going on times delta Y. So that kind of helps us out. If you want to clean it up, I notice if we're going to integrate, we notice, well, if we see a radical, might as well write it as rational exponents. So that could give us some justification. If it's cube root of Y squared, it's actually Y to the 2/3. So now you kind of have a really nice idea of what the volume of one of the disks will be. So then we could just replace it into our integral. So we still have 0 to 8 pi instead of R squared. We just simplified that there. We should have Y to the 2/3. And we still have dy. And then now you're kind of home free, because we can say, well, we know we have some experience. We can factor out the pi. And we have integral of Y to the 2/3 with respect to Y. And now I would most likely be inclined to use my TI at this moment. Punch that into your TI. You can do it by hand. It's not too bad, but we're already thinking about solids. So when we do use our TI, we get a decimal that we cannot turn into fractions. It's like 19.2000 and so on. So we can say that that is about 19.2. Still considered exact, because we are looking at, I believe it was like 19.2 and a bunch of zeros. And I think it was either a 3.7 or a 7.3. Feel free to play with it. So we can kind of say, okay, 19.2, good to go. Final volume of the solid would be 19.2 pi. And of course, don't forget the units, and they're cubic in this sense. Kind of a nice review on disk method. Just a heads up to remember the R is varying. That's why the R is the variable X. And then just being careful as to what you're revolving the solid about, or the region about. That's going to give you the heads up of your thickness, and your integration with respect to what variable gives you a heads up of why we have to solve it in terms of Y instead of X. So play around. If you're still not comfortable with that, I would definitely go over a few more before proceeding to trying the shells. Let's move forward a little bit with the idea with the washers. And I believe we did this one in 5.2, but it's not bad to review it and just kind of, you get another version of the picture, perhaps a lot better than my drawing that I originally had made. So this time we're going to find the volume of the solid formed by revolving the region bounded by the graphs of y equals x and y equals x squared about the x-axis. And so you could kind of remind yourself, okay, y equals x was the line. So we can see that right here. It's already kind of labeled. And then y equals x squared was the parabola. And we can see that labeled as well. If you feel the need to, sometimes just color coding them really, really helps us just see. I'm a little shaky there, but you understand the point from there. So one of the things, if you're trying to understand why we would use washers, is we would take this cross section, and I think I'll highlight it in red. So we have this cross section that's taken perpendicular to the axis of revolution. So there's our x-axis there. And we already kind of have a heads up, if you're revolving about the x-axis and you're using washers or discs, we know we're going to use a dx when we are integrating. So we'll have an idea there. But to give us an idea of why we'd use a washer versus a disc, if you revolve that cross section, we end up getting a disc with a hole in it, otherwise known as a washer. So that kind of justifies, okay, there's the washer coming in. And if you're going to use the washer, we go back and say, okay, first thing we do when we're trying to understand this is you want to try to set up an equation or a formula for the volume of one washer. And I'll label it just so that we know. Maybe it's just a washer. Don't pluralize it. There we go. So remember, with the volume of the washer, what we would do, it's still kind of the idea of pi r square h, kind of like a disk, but because there's a hole, we're subtracting off the empty space. And if we're subtracting off the empty space, it ends up being pi capital R square minus R square times our thickness. And so we decided, we already know that the thickness, if we're using about the x-axis, we're using dx or delta x. We kind of have everything set to go, that we know whenever we try to integrate, we're going to have to rewrite all of our r's in terms of our x's. So as we go through this, the idea is to understand what your cross-section is doing. So you want to look at the point on the curve for your particular starting point of the cross-section, which gives you your, I believe, I'll do it this way, excuse me. I've been kind of trying to stay consistent. So I believe I'm going to do the outer region purple. So you just want to understand, like, there's a point on that particular cross-section. All points are always x comma y. In our case, we would say it's x, and I believe it should be our y sub, let me see before I revolve it. Let's see what we have. The one that's on the curve, actually, I could have done it green. I'll do it green. I guess it really doesn't matter. But as I'm looking at what's being revolved, when I kind of try to understand what it looks like when I draw my cross section, it believes like the point on the y equals x squared is the smaller circle. So that's kind of giving me the heads up. Okay, that's helpful. So again, if you're trying to label it x comma y, that is true. But if it's the smaller circle, we kind of look at it in terms of y sub lowercase r. And similarly, if you want to take the edge of the other a cross section, or the other side of the cross section, excuse me, I noticed that that piece is located on the straight line. So when you draw your revolution of your cross section, that ends up drawing the larger circle. So that gives you the point X, Y, of course, but we would use capital R because it's the larger radius. So I'm just trying to understand that setup. So then you could kind of see, I copied this from the textbook. We get an overall aerial view of our cross section, so we can kind of see why we're using the certain points we're using. So this longer piece we called R, and I should, well, of course they're called R, they're the radius, but I'm looking at it in terms of capital R. So we have capital R right there. And then the shorter piece we call lowercase r. And I was going to color code that. Trying to remind myself. There we go. So that provides a bit of justification. And like we said, before we even tried to integrate, we want to try to write everyone in terms of x. So just one more time, the way I'm looking at it, if I'm trying to understand the volume, I'm trying to understand what uppercase R would be. I go back to my point where it's located. So that would give me x comma y sub r, uppercase R. And just kind of remind myself, do I have a way to rewrite R in terms of X or Y? Well, in our case, it is the Y sub R. It is a Y value that we're dealing with. And because it's located on the line, that Y value is equal to X. So we have this going on. So now we have R in terms of X. And if this is the case, we'll do this one more time with the other point. Notice that this is the lower point of the curve. This Y value is smaller on this cross section. So if we're looking at X comma Y lowercase r, that's the only reason why we denoted them this way. We just try to understand, what is this R? You've got to write it in terms of X or Y. And because it's kind of representing it looks like it's a vertical distance, just like we were earlier, we'd be looking at Y sub lowercase r. And then you're just trying to pay attention to, where is it located? What curve is it on? It's located on the Y equals X squared curve. So we could kind of see another justification of why it's equal to X squared. And it's kind of also demonstrated with the aerial view of the circle onto the right, if you're worried about that. Doesn't hurt to see it over again. So now you could kind of say, well, if I want to continue this volume of 1, well, instead of writing the cap R, we should have the X, still squared. Subtract off lowercase r, in this case is considered X squared. Still squared because we didn't touch anything in the actual formula. And again, our thickness is delta X. So then we just take a little bit of time to just clean it up a little bit of exponent rules there. X squared squared is X to the 4th. And then now we are ready to actually find the volume of the solid. So then we just have to understand, well, what do our formulas go from? So I'll write it in just so that we can get an idea. dx, because thickness is delta X. So now we're just trying to understand, are we using X values or Y values on the limits of the integration? And when you're seeing that everything's in terms of taking everything in with respect to X, we'd be looking at spanning with the X values. So everything from X equals 0 to X equals 1. So it's helpful for us to see. If we were taking with the Y, it'd kind of be the same based on the functions that we have, but always kind of verify before you proceed. Similarly, like once you've set up this integral for volume of the solid, everything's in terms of X. If you're taking it with respect to X, you're kind of home free because we know we factor out that pi, and we use our TI to calculate the exact value of the integral. Or if you have to do it by hand, you have to do it by hand. But I know earlier we had calculated this to be 2/15. Nice exact value. So finally we have our volume of this solid. We'd see it written as 2π/15, and of course we have the cubic units. So a nice quick review of pretty much a 3-hour lecture. If you kind of looked at section 5.2 already, kind of the idea of why we use washers versus why we use discs. So one more type of issue could come up. Just kind of want to help us develop this. I'm going to start looking at the idea of why we might want to use shells. So the idea of reviewing the two methods before we started on the actual content of this section is to remind ourselves that the cross sections that we were taking were always perpendicular to the axis of rotation. So that was kind of the key. So if we wanted to do this, we kind of noticed that if we were revolving about the y-axis, we know that that's the axis of rotation. We would then attempt to say, okay, that gives us a heads up right away that we're going to need to use dy in our integration. No problem there. And it also gives us a heads up that our cross section should be perpendicular to the y-axis. So if you were to draw your cross section, just like we've done here, we have a cross section that is perpendicular to the y-axis. Well, the best we could draw it. And when we try to understand how are we revolving it, well, we're looking at the two edge points and you're saying, well, that point, usually what we do is we calculate the same distance away. So if we're trying to draw a quick sketch of the cross section, same thing, what we would probably do is understand if we're looking at the other side of the cross section, you'll probably take the same distance about. So this is our cross section being revolved. So I kind of mirror it on the other side of the axis. And then what we're doing is we end up connecting the cross sections. So we can clearly see what happens here. We connect these by the best version of ovals that we can make. What do we call this? This distance right here is lowercase r. See if I can write that in for you all. And then we can see, oh yeah, it makes a bigger circle if we rotate the outer edge of this cross section around. The best that we can, a little shaky today. I'll try that again. That's still ugly. I'll work. All right, that's the best I could do for today. But this helps us see that when you look at this distance from the axis of rotation to the actual point, that is actually equal to our uppercase R. So when we have the idea of what are we going to be using, there's a hole in our solid, in our cross section, therefore the washers would be the idea. So we would think washer would be the idea. And okay, if you're going to use washer, then we go through the whole volume of 1. And we go through, okay, volume of 1 is pi uppercase r square minus lowercase r square. And then of course we'd be using delta y for the thickness. Let's draw that delta a little nicer. Okay, so if you go and try to develop this now, what we're trying to understand is, as we're looking at the r's, in both cases, the radii are varying. So I'll kind of write that on the side. Both radii are varying. So that kind of gives you a heads up of we're either using an x or y value to represent them. But when you're kind of looking at the way the radius is set up with the cross section, we notice that they're both horizontal distances. So when you kind of look at your ordered pair associated with each, I could be looking at x comma y. Same thing on the other side, x comma y. But if you want to be specific, it's the horizontal distance that we're dealing with. So that's why we kind of are having the subscripts of x sub r and x sub capital R. So, I mean, you could kind of see this with the picture. Well, if that's the case, if you're trying to name everything in terms of x, your x distance is going to be based on your y values. So let me see if I can kind of color code this with you. Again, your x sub r y is going to be associated with the curve. Your y value should be 2x squared minus x cubed. And similar, it's the same thing with the other one, but I want to point out that the x value you're actually using, it should be lowercase with the subscript because of the smaller radius. And write this one more time. With this one, I have x uppercase r sub y. That also indicates, well, that x value is related to, it's also that y value, which is 2x squared minus x cubed again. But remember, it's the longer distance. So we can do this, no problem. But if we're trying to, like, you know, it looks nice from what we're trying to understand. I have my r square, my r square. But if everything has to be in terms of delta y, we would have to take both of these equations and try to solve them for x in order for us to turn everything back into terms of y for our r's. And what's happening, I wrote it down because you know, sometimes it's too hard to write down while you're trying to understand the idea, is that if you're solving these equations for x, the ones that I've just highlighted, it ends up being a bit too hard. In fact, it's almost impossible. So we kind of run into an issue where this r is hard to rewrite in terms of the y, or solved for x, I should say. And this r is also too hard to write in terms of what we need it to look like. So the reason why it kind of fails for us, and some equations lead us to having issues, is I can kind of go back and bring you back to 5.1 a little bit. There was a rule that when we would draw our cross-section or our segment, I'd like you to notice this, that when we did draw the cross-section, it did touch the same curve twice. So it kind of ran into each other. So cross-section here touches the same curve. Our same function twice. And that curve is the y equals 2x squared minus x cubed. And you could kind of see it when you draw the picture. But the reason why it's giving us trouble, and what we would do in 5.1 is we would avoid this at all costs. We always said, if it does that, we want to try to take the cross section or the segment, we want to take that a different way. So instead of being perpendicular to the y-axis, we would say, oh, let's make it so that we make it perpendicular to the x-axis. So if we're trying to avoid this situation, and this is what happens, it makes the equations impossible to rewrite and calculate the integral, we run into now deciding, let's take the cross-section a little bit differently. So let's instead make it parallel to the axis of rotation. So that's a little different than what we've been dealing with the washers and the discs. So if you do this, what ends up happening as you turn the cross section around, you get a cylinder with a hole in it. But the problem, it's how it's different from a washer. It looks like a washer, it's just thicker. What's happening is that the height is going to be varying depending on where you drew your cross section. So I'll show you a picture in a second, but not only is the radius varying, see if I can draw this kind of from here to here, that's R. Depending on where you take your cross section from, the radius will vary because it could get wider as we go over here, and it gets smaller again if we go a little bit more on the curve. But also, as you take a different point along the curve, wherever it happens to be, you will also notice that the height will vary this time. And that's different from a disc, because the disc, the thickness was always the same. So there's kind of two somewhat variables coming along. So what we end up doing, instead of playing around with how everything keeps varying, we end up taking R as the average radius of the shell, because there's two radii going on. They're varying along the way. If you're taking R as the average radius of the shell, I'll kind of keep that in mind. H being the height of the shell, we're kind of used to that already. Then what we get if we want to try to find the volume of one of these shells, we're looking at this formula, which is somewhat similar to what we were looking at, 2 pi RH times thickness. And if you kind of want to know, like, well, why is this the case? Why is it not the same as the washer? So I could kind of give you a little bit of a why. What you're actually making is not really a 3D solid, as we did when we made the washers as well. What you're actually looking at is kind of like a slice of paper that's being rotated around the y-axis. So the shells are slicing up the particular x-axis in this case, but they're rotated about the y-axis. When we think about this, it's a piece of paper that's being rotated around. So it kind of, I'll do my best to try to draw a 3D version somewhat of it. And when we talk about paper, if we're playing around with, going from the cylinder, see if I can draw this a little nicer. It's somewhat nice. What we're looking at is this rectangle. It wraps around the cylinder, and it originally has the height h. That's no problem. We have that the same. But what's actually going on is that this piece, if I can see if I can color code it in orange, this piece right now is turning into the circumference of the circle that you're making when you're wrapping this paper all the way around, and circumference of the circles, 2 pi r. And so that's where the 2 pi r times h comes from, because you're actually finding surface area. And surface area, we're looking at a rectangle, area is length times width, 2 pi r times h. So it should make sense geometrically, but you really want to take that idea as it's not that you're revolving a 3D object around, you're actually revolving a two-dimensional object around, and that's making it's like a piece of paper. So if I could kind of make it a little prettier for you, just to understand why. We kind of try to give you some pictures. I took this from the textbook because I thought they did a better job. There's no way I would have been able to draw this myself. So just kind of notice if you're revolving a region around the curve, what happens, even if you pick any cross section, you're going to revolve a piece of paper around the axis. And then what happens is if you take more, so here if I can say, here's my volume of one shell, here's one piece of paper. And I wrote it this way, we'll get to why in a second. If we take more cross sections, kind of like what we're looking at the middle figure, you end up getting sort of like the idea of a few more pieces of paper wrapped within each other. We end up having maybe the volume of a finite number of shells. So we can count how many shells we have. And so for example, n, the number of shells we have, what do we have? 1, 2, 3, 4, 5 shells. That's kind of nice to see if we drew 5 cross sections and revolve them. So like 5 pieces of paper nested with each other, kind of like wrapping paper. And then if you want to get crazy and say, well, what if we took an infinite number of shells? We slice this x-axis up infinitely from A to B. We are getting this part. And this is what is justifying why we're probably going to result to integral. This is a limit definition. Let's see if I can help you with this. So very similar to how we were dealing with integrals with areas under curve. This limit definition is taking care of infinitely many shells. So what we end up kind of looking at, in a sense, this solid that we've made, it kind of looks like a toilet paper or toilet paper roll. If you can kind of picture that, how thinly sliced all those sheets are. But if they do make volume as long as you have more sheets revolved around your axis of rotation or revolution. So what ends up happening, they make the same jump, and this is, we don't take so much time developing this because we just say, we go straight towards the integral. But we remember that when you have limit definitions and you have summations, if you want to take care of everything, they all eventually approach the idea of the integral. And so now we finally have the nicer versions, if I can highlight them. It's basically the volume of one solid. If I could write straight, there we go, 2 pi RH delta x. Notice that's where we got the volume of one of the pieces. And the same idea, 2 pi RH delta y. So it kind of depends on what you're slicing up, just like we did in 5.1. So if I could kind of draw a quick picture just to kind of give you an idea, remember the cross section that we're dealing with is parallel to whatever axis we're revolving around. So if I can draw a quick picture onto the left, I'll do my best. You know, whatever region we're looking at, we're kind of picturing a piece of paper that's being revolved around the y-axis in a sense. And so however many shells you make, you can make more if you need to, kind of can see what's happening. But each of the shells seem to be slicing up the x-axis. So here, the shells slice up the x-axis. If that is the case, if they're slicing up the x-axis, just like we did in 5.1, we're using delta x. And so notice we're revolving about the, if I can write straight again. So we're revolving here. We're revolving about the y-axis. So that's kind of our axis of revolution there. So when you make your shells, they slice up the x-axis. That's why we're using delta x. And just to remember, the cross section that we're taking is parallel to the y-axis. So that's different than what we're used to. And similarly, we want to do this the other way. Just kind of draw this on the right here. Let's say you have a shell, or I'll just say piece of paper, and you're revolving about the x-axis. Well, what does your piece of paper do? Your cross-section revolves. So we're seeing it this way, and we can make more if we need to, just so you can see a little better. Here's another shell. Notice that's why I use the book to kind of demonstrate how pretty that would be. But if you kind of can look at this a little bit clearly, here, your shells, they're slicing up what axis? So they will be slicing up the y-axis. And that happens when you're revolving about the x-axis. And that kind of justifies, okay, when we do that, the cross section that we actually took is parallel to the x-axis. So it's the idea of shells take cross sections that are parallel, washers and discs take cross sections that are perpendicular. So hopefully that justifies it a little bit as to why we're using dx versus why we're using dy. A little different than the other two methods from 5.2. But I am sure we all need to practice it in order to be a little bit more, how do you say, feel a little more comfortable with the whole process. So I'm going to take you back to example 3, and we're going to go through this. And by the way, we're finding the volume of the solid obtained by revolving the region bounded by these graphs about the y-axis. I believe I drew it up here, but sometimes I missed. Let's see if I can get that down. Yeah, right here. I'll put this closer just so you can see the region. The more complicated the curves get, sometimes the less likely we're going to be able to see our particular regions being rotated. So now if you look at what you're getting, it kind of gives you the idea of why for sure we're not using discs. You could kind of see that there's a hollowed out part in the center. And also, besides the fact it's kind of justifying ourselves away from using washers, not only couldn't we couldn't figure it out how to solve it for X to make everything in terms of Y, but you can kind of see that the radius is varying and the height is varying as you're going through a lot of these shells. So if we do this, finding the volume of the solid obtained by revolving the region bounded by these graphs about the y-axis, if we're using shells, sometimes I'll note to myself, with the shell, it will tell me to use, if I can write correctly, I guess I'm having problems today, here we go. With the shells, we're going to be using what's parallel. So you're thinking, well, what's the y-axis? The y-axis is, we're revolving around here. Oops. I'll highlight that for you. And so your cross section has to be parallel. So you're thinking, what axis are we slicing up? We're slicing up the x-axis, so we're going to use delta x. So now when you say you go through this, okay, volume of one shell. And I'll rewrite it as shell. You don't have to because you'll kind of know what you're using. Shell, there we go. It's always 2 pi RH times thickness. And with the thickness, we already know 2 pi RH times delta x, no problem there. And so now it's our job to we kind of have the idea of the two variables. Not only is the radius varying depending on where your cross section is. So the radius varies, but also wherever you draw your cross section, the height is varying. So that kind of gives me a big heads up as to why I would use shells. In fact, the height ends up being, if you're kind of understanding the way it's set up, the height actually ends up being a function of y. No matter where you draw it, the vertical distance is going to fall along the curve. And the curve that you're trying to identify, it's given by 2x squared minus x cubed. So take time to develop that. If you want to draw like mini cross sections, you can kind of see, oh yeah, the height is varying and it's based on whatever the curve is. It gets really big towards the middle, and then maybe when you get closer to 2, the height goes back down. So I'll erase that because sometimes that adds a little too much noise to the picture. The other idea, if you're trying to pay attention to what we're dealing with, is that if the radius is varying, you have to understand, well, what is radius standing for? So feel free, you can kind of see it already that based on the point that you're using, it still goes to xy. The radius is the average of all the shells, or the two that you're making. Sorry about that. My radius is actually a horizontal distance. And in our case, it's varying, but it's equal to your x. So that kind of gives us an idea of how we can replace these. And now I'll color code it because I think I called radius. So I'll do this for you guys. Okay, so remember with shells, we use delta x or dx. Thickness is delta x. My radius is varying. So when I want to find the volume of 1, the radius is already x. It's in terms of delta x, so that's already good. We're happy with that. So we'll replace x into the r part. Now the h part, if the height is varying, the height needs to be in terms of x. It's a function of y already in terms of x. So this is why we're able to replace the 2x squared minus x cubed into our volume of 1 shell formula. So that makes things much nicer. We never end up having to solve for x. Everything's completely nice. The only thing I would recommend is just cleaning up the algebra just a little bit. So that's probably just distributing that x through might make your life a little easier. So we should have 2x cubed minus x to the 4th, and then delta x. And yeah, you could distribute the 2 in if you wanted, but eventually it's a common factor. I'll probably just factor it out when I make the volume of the solid. So now we're ready. So remember, with the volume of the solid, you can set up your integral. It's always taking the volume of 1 shell and using dx instead of delta x. And then because you're using dx, what you're trying to pay attention to is your limits of integration have to deal with the x part. So if you could kind of look at what are they trying to help us out with, according to the picture and the regions, we could eventually figure this out. The x looks like it starts at 0. And we could actually plug this in because y equals 0. If y equals 0, the x has to be 0. And at this point, the x also has to be equal to 2. So we're kind of getting our slices going on. And you could also have done this. You want to find those y-intercepts, or those, excuse me, the x-intercepts, my bad. You could actually find those if you didn't already have the picture in front of you. Your x-intercepts, based on the way the region is given, that's where your y is equal to 0. So this is where you see that, oh, okay, I should have, if I take out x squared, I should have 2x squared, 2 minus x. So that's where we're getting x equals 0 and x equals 2, just in case you're worried about that. Sometimes the picture makes it a little obvious to us, but we need to make sure that we're clear on what's being rotated around or revolved around the axis. So my friends, once the setup is taken care of, like I believe finding the volume of one shell and rewriting everything in terms of x is the roughest part, we can then say, no problem. Let's factor that 2 pi out. Let's take the integral. And it's not horrible to do by hand, but we do have that technology waiting for us with our TI. I believe if you want to type that in, that should give us 8/5. I always like the exact answer. And usually exams and quizzes ask for exact answers. So we have 2 pi times 8/5, which would give us 16 pi/5. And don't forget its volume, so it's cubic units. Voila, nice way to do this. So shells kind of seem complicated at first, but you'll find that it makes the algebra and the calculus a little nicer. I want to walk you through a few more so that you could kind of get the swing of things, and then hopefully you'll be prepared to take on this section. So let's go a little further. With example 4, I'm going to find the volume of the solid resulted from rotating the region enclosed by y equals 1/x, y equals 0, and x equals 1, and x equals 10 about the y-axis. So I'll draw y equals 1/x. If they're only asking us to go from x equals 1 to 10, you could draw your, you can use your TI to help you understand this, but y equals 1/x, at least part of it, you can kind of say, oh, that's what it looks like. But if we're only dealing with going from 1 to 10, then you could kind of find your particular x values. I'll probably have to draw this a little bit exaggerated, so excuse me on that part. But if you want to find your particular y values now, you can, but we're only looking at the particular region. So this region from this region, kind of L-shaped in a sense. So if we were to maybe shade it just so that we have an understanding, we can say, okay, we're going to revolve this region about the y-axis. So that's our axis of rotation. And because we're trying to understand why would we use shells, again, if you tried to go perpendicular, you might be able to do it, but let's kind of go with what we're trying to understand. And actually, I might even show you my setup of why I'm trying to make sure I'm using shells. When I do the rotation, it looks like it just kind of leads you to understand that the inside is empty. So that narrows it down to washers or shells. And then as I'm trying to understand, it's not going to be a washer because the height is varying according to the cross-section used. So I don't know if you can see that in the picture, but I can draw the cross-section for you and we can kind of make a note, but that's something that we have to pay attention to. So let's draw that really quick. So a little bit of an idea, and it does help to be able to visualize it, but drawing the cross-section should help as well. So we're not using a washer. And the reason is height varies according to cross-section used. So if that is the case, that gives me the idea shell And when you're dealing with shells, we're going to use parallel to the y-axis. So the cross-section itself, if we're going to draw that cross-section, parallel to the y-axis, we're slicing up that x-axis. So that's why we are using delta x. So let's draw this just to make sure we're okay. What I like to do is kind of keep the idea of where the point is. So I'll do that. I'll draw the point on the curve. And that curve is x, the point is always xy, you know that. But if you want to draw your cross section now, you're saying, okay, we'll go the same distance out, about. And we know that we'll be drawing. So it looks like we have this cylinder going on. Also, the end of the cross section has the idea. And so now we have justification of our R. Radius is varying. It's kind of like a checklist I make with myself. The radius varies, and also depending on where you draw your cross section, you can kind of see the height will change according to where it's located. So the height varies. So sometimes you either know you're going to use shells just because you can picture the solid, or if you want to draw your cross section and then maybe draw another one and kind of compare your radius and your height, it's going to help out a lot. So the radius varies, the height varies. It's kind of the justification. We're going to use the shell. And if you want to pay attention to what the height is doing, the height's varying and it's based on the function. So height varies and it's based on function y. And the function is y equals 1 over x. So kind of keep that in line. So now you're kind of ready. Okay, we could do this whole volume of 1 business. And we already know it's 2 pi RH times thickness. And we've established that the thickness is delta x. So now I should have 2 pi. My R is equal to x. It's a horizontal distance based on the point that I'm using. My H is a y value. Maybe I should color code it just so that you can see according to what we did. So radius is an x value, horizontal distance. The height is a y value, vertical distance. And so you're just trying to understand if it's in delta x, anyone that's already at x is good to go. So we're happy with the 2 pi x, but the y is what has to be changed. But we're kind of lucky because the y is already solved in terms of x. So we're going to change this to 1 over x. Still got delta x. But now if you notice you want to clean this up a little bit, what happens to the x's? I mean, just nicely, we end up getting 2 pi. They divide out delta x. So now if you're ready to do the volume of the solid, I'll do it this way. What do you have? The integral 2 pi dx. And then now you're just trying to understand, what are my limits of integration? If I am slicing up the x-axis, it should be going from x equals 1 to x equals 10. Well, you can either do this by hand. It's not too bad. Might as well. We're pretty much, what do you call it? It's a constant. Integral of a constant means we just attach on an x and we evaluate it from 1 to 10. So what does that give us? 2 pi. And then what the x is, fundamental theorem of calculus, 10 minus 1. Have a little fun here. I'll go horizontally. What do I have? 2 pi times 9. And that's 18 pi. And don't forget, we're finding volume, so it's cubic units. So sometimes the shell's not bad. You can kind of see what works for us. I like that. Let's pick out another one. Okay, so now we're going to find the volume of the solid. resulting from rotating the region enclosed by x equals y squared, x equals 0, y equals 2, and y equals 5 about the x-axis. So the only thing I always remember is, okay, make sure we understand we're revolving about the x-axis. And I know we're in the shell section, so we're probably using shells, but let's justify why before we just jump into that. Sometimes it helps just understanding pictures. I notice when I have things in terms of x, sometimes it's helpful to rewrite it so that you're solving for y. So I know x equals y squared, it's a sideways parabola. That's y equals plus or minus square root of x if you're kind of worried about that. So if that is the case, if we're trying to draw that, you have the top half, kind of a square root function, and you have the bottom half. The best I can. That was ugly. I am not liking that one. Here we go. Sometimes I blame my left hand, but I'll try. So you have a sideways parabola, we're happy, or those sleeping parabolas. They want us to look at x equals 0, y equals 2, and y equals 5. So we're not just looking at the region between the curve and the x-axis this time. X equals 0 is the y-axis. So I'll see if I can, I'll draw those in purple. So x equals 0 is here. I said purple, and I drew in blue. So x equals 0 is right here. Right now I don't have a region yet. Y equals 2. We'll kind of justify it about right here. And then y equals 5. Another horizontal line. The best we can. Obviously that doesn't look really pretty. I'll work on this. But that is y equals 5. So if we're talking about the region that's bounded, that looks like this particular region. So it's not what we thought it was going to be. So I have this region that I do have to rotate. And when I kind of look at it, I'm noticing that, yeah, it doesn't look like one of those nice regions. If I rotate that region, I can give you this. You'll notice what we end up getting. That's the entire solid now. So that kind of justifies what's actually going on is that your radius, it tends to be constant for a little bit, but it starts to vary as you move towards larger values of x or larger values of y. Also, the height of your particular shell is going to vary. So let's kind of make sure, let's draw a cross section and really judge this for a second. If we draw the cross section, it should be parallel to the axis of rotation. That's according to the shells. So we're going to use, we know we're going to use delta y. But when we have our cross section, we know we're slicing up the y-axis this time. You can then kind of look at what the regions are. So let's look at this. So let's look at the point on the curve. You look at the two values here. Okay, so that's rotating about the x-axis. What do we have to do? Take it down to about the same distance for each of those points. I'll eye it for you all. Should draw that straight, right? There we go. And then you have your mirror image of the rotation. And then we can see as we connect, it gives us an idea of what we're making. And so now we have this hollowed out version. You would say, okay, we know there's a hole. The reason why we do not use washers is because the height varies. You could kind of see where it's located. As you move along the function, whatever cross section you take along this curve, the height will get taller or shorter. So the height varies. And if we want to understand the idea of what we're looking at, you could look at the idea of what point we're looking at. Is the height a horizontal distance or a vertical distance? Well, in our case, it's a horizontal distance, so it should be taking the x value. And the radius, we're trying to understand what this radius is doing. It's the distance from the axis of rotation to the actual point. The radii or radius. The radius varies. And if you want to look at it, it's a vertical distance. So vertical distance means it's y. So that's kind of helping me with understanding what's happening with the point itself. So if I can make sure I mark this point, I'm looking at x, horizontal distance, and y, vertical distance. So if you can kind of map your radius and your height to whether it's an x value or y value, that's a nice heads up there. Kind of while we're understanding this, we're giving the justification of why we use shells, but now you can go into, okay, what's the volume of one? We know 2 pi RH. 2 pi RH times thickness. And who's our thickness? In our case, we call it delta y. So you have 2 pi RH delta y. Now, if we just kind of justified that our radius is y, our height is x. I wanted to color code that though. We now have our setup for the most part, and we now know which one we're supposed to change. If we want delta y, we've got to change the x. And so then we have to see, well, what is x related to? We go back and we say, well, where's it located? It's located on the curve. And that's usually kind of nice justification. But just look at where your point is. And that point is located on the curve x equals y squared. So that gives you the relationship. Instead of writing x, we're going to write the y squared. Got to have delta y. So we have 2 pi y times y squared, delta y, and to clean it up a little bit, 2 pi y cubed. Why did I say delta x? I guess I'm thinking ahead. But it is still delta y. Things don't change in the middle. So 2 pi y cubed delta y. And now we're ready to find the actual volume. So the volume of our solid is equal to the integral. If it's going to let me draw, it must be out of battery. Something's going on with this section, but we'll work on it. 2 pi y cubed delta y is dy. Now what we want to do is understand, which axis are we slicing up again? Our region takes a span of y equals 2 to y equals 5. Nice that they gave us those functions. So that's where our limits of integration are. And after we have that settled, now we know, no problem. We're going to factor out the 2 pi, make our lives easier. And now we can take the integral from 2 to 5 of y cubed with respect to y. And yeah, you can do this, if you'd like by hand. But with the TI, we end up getting, let me see, I'm typing it in myself as I go. We have math, function integrate, type in my limits of integration. Okay, it should be 609 over 4. Wow, it's ugly, but it's still giving it an exact answer. So I have 2 pi times all of that. So we just reduce the 2 and the 4, so we should get 609 pi over 2. And because it's volume, cubic units. Voila. So moral of the story, whenever you're doing these revolutions with solids, is really pay attention to the points that are making up your radii and your heights. It really gives you a heads up as to what has to change versus what can remain the same. And based on your delta y or delta x use, you know which one to modify. So I'll walk you through. I think we have a couple more examples and we're almost there. So sometimes when you take tests or quizzes, they want us to demonstrate that we know a particular method. So even though certain regions can be calculated, at least the volume of solids can be calculated using different methods, maybe they want us to use shells for this time. And then you'll see in part B, they want us to use washers. So let's go through this. We have, we've actually, I believe we've done something like this already in 5.2, but it's not bad to help ourselves. If I want to rotate the region bounded by y equals square root of x, and then x equals square root of y, I do know from our past experiences, I'm going to explode this a bit. But this is y equals square root of x, and x equals square root of y. That's the other way around. We just kind of played with it, but kind of looks like the version here. So you can kind of notice already, there's more to them. Feel free to extend, but you'll see right away that they intersect at a certain point. Very nice point right here. And they also intersect at 0, 0. So you can always play with it if you want to use some algebra, but we already demonstrated this in the past sections. So we already have a feeling that the x values, we go from 0 to 1. And also, it also happens that the y values go from 0 to 1 as well. So whatever we decide to integrate with respect to, we're pretty much set. So if we decide to use shells, we have to remember that the cross section should be parallel to the axis of rotation. So who are we doing? About the x-axis. Okay, so x-axis is this. So the region itself, it's kind of this almond-shaped region. So that region is being revolved around the x-axis, and the cross section that we would be using, if we use shells, cross section has to be parallel to axis of rotation. So if you want to draw that, the axis of rotation is x. So my cross section is right here. So now what I like to do with all of this is I could kind of talk about the endpoints of each section just to help you. They're all considered x comma y. Yes, that is true. But you also know what function it landed on based on our color coding and such. So in our case, we're dealing with the x equals square root of y function where that right-hand point is. And if I pick the other side, it's on the blue curve, that's also an xy coordinate. And we know that one is y equals square root of x. So I want to be careful when I'm kind of trying to remap those later. So I'll get back to that. So let's do ourselves a favor, just kind of keeping in mind what we're rotating. When you do the rotation, what do we end up doing is we kind of map everything down about the same, the best we can. So here I have my mirror image of my segment. I'll draw kind of like a little less pronounced. So the mirror image of my segment or my cross section, and then I can use this to draw my shell, my one shell, I guess. Okay, so now you kind of just picture it and you're saying, okay, first thing we want to deal with is we could kind of see the way the radius is situated. The radius is a vertical distance. So we'll keep that in mind. Radius, vertical distance. So it kind of tells me that it's going to be related to y in some sense. But you have to kind of say, well, where does it locate? Which function is it on? And it depends. We'll get there. The height is varying as well. The height this time, it's relating to horizontal distance. Okay, so height, horizontal distance. I know we're going to be dealing with x's. Okay, so let's look at this a little bit more carefully. When we deal with r, the vertical distance, which is also y, in both cases, the r values are the same and they're based on your particular functions. So they're both y, no matter what. But the height relates to the x values, but we have to be careful because it's kind of situated away from the y-axis as well. So remember, we're just looking for that distance. And so it's not just x, it's both x values that we have to deal with. In fact, if we're talking about a distance, we're trying to say, what's the difference of those two x values? So this is where we have to kind of say, well, there's two different points. Let's keep this mapping back one more time. It looks like y is the same no matter what. Wherever you draw your segment, the y values are going to be the same. So what ends up happening is the x values are different. One's smaller than the other. So then you could kind of remap it. We used to say like x of lowercase r, x of uppercase r, but x doesn't have any relation to radius, so I don't want to confuse you. What I will do is make subscripts. I'll make the x sub 1 the smaller point, and I'll make the x sub 2 the larger point, or I should say the larger distance away. So if you want to talk about both x values, what ends up happening is the horizontal distance is the difference of the two values. And as long as we're naming the x2 as the larger point, we don't have to worry about absolute values. So it should be the difference of the two values. Okay, so let's see. Let's go back and see if this matters or not. First thing, volume of 1. So volume of 1, we have 2 pi RH times thickness. And so if we remember our thickness, right away, if we are parallel to the x-axis, we're slicing up the y-axis. So our thickness is delta y. It's nice to kind of get situated. Now you can kind of go back to your mapping. Whoever you called r in both cases was the y value. So we can say, okay, no problem. That's y. H, and maybe I'll do it in orange because I had it in orange. H has to do with horizontal distance. And we already figured out that it's the differences of the two x's. So we said x2 minus x1. So we kind of have the idea. But what do we need? Delta y, or dy, means everyone has to be in terms of y. So the very last idea is trying to understand what is x2 and x1 in terms of y. So we're going to change this. And this is when I start to relate the functions back to where the points are located. So if I can do this, x2, let's look at this one more time. Where's x2 located? It's that red curve. Okay, so let's kind of map that out. If I have x2 and a y, that maps to the red curve, and the red curve is the x equals square root of y. That's the first thing I always look at. And so if I'm kind of looking at it, well, that means that x2 equals square root of y based on my ordered pair. So x2, when I replace it back in, this has to be square root of y. And x1 is similar. I'll kind of write this out. Looking at the point that I'm on, x1 comma y, that's on the curve y equals square root of x. So if I'm trying to rewrite it in terms of y, I need to solve it for x. What is that? Y equals square root of x1. Who's x1? Square both sides. Well, let's make that prettier. Square both sides, so we should get x1 equals y squared. So that's going to get replaced. Don't forget, we still had the minus sign, and we were trying to make everything in terms of delta y. So whenever I'm stuck, what I always do is I always kind of think about, okay, once I have my volume of one set up in terms of radius and height, and I'm not using r and h anymore, I'm using x's and y's, I go back to who is my thickness, delta y. And then once I understand it's delta y, anyone that was not a y has to be rewritten in terms of y. I then go back and look at where they're located on the curves. And I use my points to give me a reasoning as to how am I going to rewrite them? Which curve am I using? And do I have to solve for y or do I not? So kind of play with that. If you're not comfortable with that, don't move on until you can really do this. But once you have this all down, we're good to go. What we end up doing now, clean it up a little bit. You can kind of see, we don't like radicals. What do we have? Y. My left hand, again, betrayed me. But here we go. We have y, it's still y. Square root of y is y to the 1/2. I got minus y squared, delta y. And then we just say, let's see if we can distribute that y through. It's going to make the integration easier. I suppose if you're using your TI, you could take a little less of a liberty here. But I might as well go through it since I've already committed to this. So this will be y to the first times y to the 1/2 is y to the 1.5 or 3/2 minus y cubed delta y. And I think the only downside of not simplifying before you start integrating would be if you have to do it by hand, it makes life rougher. But sometimes if you don't simplify and you're using your TI just pauses a little bit more. So I guess it wouldn't matter too much in this case. So now we're ready. We're going to find the volume of the solid. Move over here. So the volume of the solid, the integral, 2 pi y to the 3/2 minus y cubed with a dy. And then you're just kind of paying attention to what are the limits of integration. In any case, whether you're integrating with respect to x or with respect to y, they still are both going from 0 to 1. So same story, no problem there. What you might consider doing is factoring out the 2 pi, using your TI to integrate, or you could do this by hand, no worries. But in the end, we end up getting that is 3, let me make sure, typing that in with respect 2, yep. So we're gonna say enter, we should get 3/20. Nice little fraction there, but it's still multiplied by 2 pi. So in the end, we should get, doing a little bit of reducing, making it pretty, 3 pi over 10. Don't forget the units. So be careful. Again, when in doubt, map back to your function, look at the ordered pairs and analyze it that way. They didn't call this analytic geometry for nothing. That's exactly what you're doing when you're viewing graphs. Okay, so ideally, if we moved on to part B and then we notice, okay, we already know the volume is 3 pi over 10 cubic units. I'm crossing my fingers and I'll know I did this right if I end up getting 3 pi over 10 cubic units once I use the washers. So just kind of the idea, if you end up using washers, we're going to remind ourselves what the cross sections do. Cross sections with washers are discs. It should be perpendicular to the axis of rotation. So these are the same pictures. Again, we'll go with the y equals square root of x. The x equals square root of y. And then we notice they are still have the same intersection points, 0, 1 in either case, wherever we have x's or y's. And we're still rotating this region. So this region itself is still being rotated about the x-axis. And so if we're looking at this, the cross-section has to be perpendicular to the axis of rotation. So if we were to make our cross-section perpendicular to the axis of rotation, this is what it looks like. Now you want to pay attention to the edges of your cross-section. Particularly just understanding, you know, where is it located? Yes, it's an x value and a y value, that is true. But we can be more specific in a second. Similarly, your other end of the cross-section, that's an x value and a y value on the blue curve. Just trying my best to see if I can color code so we can make that connection. And now when you want to draw your washer, remember we're trying to draw a quick reflection so we can kind of see that, go about the same distance to draw your other point. So we should have this happening. And same story. Take a little bit of the same distance for your cross section, your other points, so then we can kind of see the reason for the washer. Now, this gives us an idea. We know that if we are using washers, we have the volume of 1. That's equal to pi uppercase R square minus lowercase r square times thickness. And we also have an idea, the way things are set up, it looks like our distance of the smaller circle, or the radius of the smaller circle, is lowercase r. Lowercase r. And then the distance of the larger radius is uppercase r. I don't know if we can, I'll do my best. So I have an uppercase r as well. So that's why I'm just color coding just to make sure I replace it. I will replace this in a second. I also want to deal with the thickness. What are we slicing up? If we're perpendicular to the axis of rotation, we are slicing up the x-axis, so we should have delta x. And pretty much when you're using washers and discs, whatever the axis of rotation is, ends up being your dx dy. It's the shells you have to kind of worry about. Okay. All right, so we're almost there. Now, remember how when we wrote our x and y points, they're clearly not the same values. It does look like the x values are the same, but what is changing is the y values. One's taller than the other. And we could kind of now look at the ordered pair x, y, just writing it to the side so I have more room. And I notice the y value is different, and it's the taller y value. That's why I have the y sub r. So that's kind of where my idea is happening. So that's a y, a vertical distance. So I have y sub r, still squared. Similarly, if I look at my other point, the x values are the same, but the y value has changed, it's smaller. And so that's where we're getting y sub lowercase r. And don't forget that's squared. So then I'm saying, okay, well, that would be great if everything was in terms of y. This is now where I have to write everything in terms of x. So we're going to have to just go through our points again one more time. So we want these in terms of x. So we'll do that. Just look at where your points are located and what curve they're on. So I am on my blue curve for x, y sub capital R. That's what I'm just kind of analyzing there. So my relating equation for that blue curve, that's y equals square root of x. Well, that also means that y sub r equals square root of x based on function notation. That's a relationship. So that piece right there, because we're trying to write it in terms of x, that piece will now be, instead of y sub capital R, we're going to have a square root of x. And just so that we don't get too crazy, sometimes it's helpful to just rewrite everything you haven't used. Okay, so same situation. We are now going to look at our curve, our red curve, and understand the equation of what point that is on. That is x equals square root of y. Well, if you write it in terms of x and y, that's the point. But if you have x and y sub r, it should be square root of y sub lowercase r. So now we just square both sides, and we actually get who y sub lowercase r is. So that allows us to now change that to x squared. And don't forget, it was already squared. So you have everything in terms of x now. You have a delta x. Clean it up a little bit. We have pi. Now square root of x squared, very friendly. That's just an x. We're happy there. X squared square is x to the fourth. Still delta x. So now we're pretty good. We want to take the volume of the solid. So we're going to take whatever the volume of 1 is, throw it inside the integral, or integrand, I should say. Instead of delta x, it's dx. And then you're just saying, who are my limits of integration? Everything's in terms of x. So I should be using 0 and 1, because I'm slicing up the x-axis. And so you'll kind of notice it's starting to look the same. We're going to factor out a pi. Take the integral from 0 to 1 of x minus x to the fourth with respect to x. Take our time with the ti on this. Notice with the ti, if we press the math key, function integral, put your lower limit in, your upper limit in, type in your integrand with respect to what variable, press enter, and we have 3 over 10, but we still had a pi. So what do we get? 3 pi over 10 cubic units. And then just check. And what always makes me nervous is, did it match the other one? It should if it's the same cross section, same rotation. It does. Isn't that nice? That's beautiful. So you can kind of see that's a trickier one. It's good to go over together, especially when it comes to mapping the points to their actual functions and replacing the radius with their appropriate variables. That's something that takes a little practice. So that's where the homework comes in handy. Sometimes just listening to me doesn't really click until you do these again. Or sometimes what I used to do is I would rewrite my notes and see if I can explain them in my own way. And then I have a better set where I can fully understand them. But do whatever you can. You do see these in Calc 2 again. And then rotations and visualizing 3D, Calc 3 comes back. So it's good to know it now. That way you don't have to work so hard later. So now that we've kind of talked about all three methods, I just kind of want to go over a rule of thumb that might help. So when you're making your decisions. We talked about this with 5.1 and understanding about touching the curve twice. So I'll just restate it. It's really good for formal notes. I'm going to say as long as anywhere in the cross section the cross section is drawn, if it hits two different curves, for lack of a better word, I'm going to say that is good. Then I will kind of follow this up as if your cross section hits the same curve twice, for lack of better word, we will just say bad. That causes trouble. So that should give you a good idea. So then you kind of say, okay, if I know, depending on what I'm looking for, should I be perpendicular? Am I drawing it perpendicular to my axis of rotation? Or I have to draw it parallel to my axis of rotation? Then that justifies why I'm using a particular method. So just kind of with our last particular example that we drew, remember we had the almond-shaped region, just so that we can see this. So you had something like this, you had your region, and just kind of understanding what your methods are doing. And sometimes it matters to understand what region is being rotated, because it could change. But if you want to draw, let's say we draw and we want to rotate around, let's say we want to rotate about the x-axis. That's my symbol for rotating. So if we want to rotate about the x-axis, we'll try it. Is this more of me of just trial and error? Let's go perpendicular. Is that good? If we go perpendicular, can we do this? Yes, it hits two different curves. We are good to go. So that method, when we went perpendicular, that method was the washer. So that's good. Can we do parallel? That's the next question. Let's see. If you draw it parallel, no matter where you draw your cross sections, do you hit two different curves? Yes, you can. So that also justifies that you could use the shell. So let's say we have another function. So we'll have something like this. And let's say we're going to rotate about the y. And if I do that, it's helpful sometimes just for me to understand my axis of rotation. I always lose track. And then it always depends what region you're rotating. So let's say we're going to rotate the regions between these two curves. That's why I always say shade the region so you see it, because sometimes it's not what you think it is. So first things first, if I'm going to rotate, what is it? Parallel? Perpendicular? Let's see. Okay, so perpendicular to your axis of rotation. Let's kind of think about that. Can we do that? If we make the solid, it looks like you can. So what can we do? It hits the curve twice? No, we can't. So we should say what? What do I want to rotate about? Oh my goodness, what's wrong with me? I should probably have rotated the region the other way, but it's okay. I'll go with it. With the disc, we're in good shape. I'll keep it this way. Okay, so if I want to rotate the cross-section parallel, this could be an idea. We could try it, but what happens? If we rotate parallel, it would work, but shells will end up getting the particular, I think it's going to be a little harder. So shell could work because we're going parallel to the axis of rotation. And also, you could think about this the way the curve is going. We could be using, it's possible to use discs, but since you're hitting the same curve twice, you just have to be careful of what the orientation is. It could work out quite nicely as well. So I'm going to say disc here too. It does hit the same curve twice, but what happens is you end up having such a nice curve, I should say, whereas the x equals, so a nice little parabola, those tend to be easier to solve for x or for y, depending on what you need. So I'll go with that. And again, we can kind of change our minds. If, let's say we take our, I think we had a reasonable function. We did something like this, and we wanted to rotate it about a line right here. That's an x value. The issue would be here is we can try to use washers by being perpendicular. But we ran into issues when we had to find these values because the radius varied and the height varied. We had a hard time solving that equation for x or for y. I think it was already solved for y, so we had a hard time solving for x. So this would be the case where this doesn't work. Touch the curve twice, we kind of have a caution. I probably should write the curve down again. There we go. So now we would say, maybe it's better to use a shell here, because that way when we rotate, we touch two different curves. So my method of choice would be shell, or shells, that's what you want to say. So practice, practice, practice. I'm going to do one more with you with this same idea, and then we'll get the hang of it. And I think we're going to be good to go with this section. So one last example to go. It kind of is the same as what we were dealing with earlier, but this time we're going to switch it about. We're rotating about the line x equals -1. So I'll do my best to, I'll blow this up quite a bit. So that's the line x equals -1. That's my axis of rotation. And if I know that's my axis of rotation, next thing I want to do is make sure I have the curve down. We've done this curve already, so I'm going to take some liberties. And it has a behavior from 0 to 2 that we kind of like. So we're going from x equals 0 to x equals 2. At least this happens to be those nice intercepts. And then we have our shaded region. So we already determined if we try to slice it perpendicular to the axis of rotation, it hits the curve twice, it's harder to solve. So this is where we say, all right, let's take our cross section parallel. This gives me a heads up. My cross section is parallel to x equals -1. Otherwise, we're hitting the same curve. So that tells me I'm using shells. And that tells me also I'll be using delta x as the thickness. So now we have a very wide rotation, so please bear with me. What I end up doing, I just see the distance, kind of looking at the same distance here, the same distance here, to give myself an about idea of what I'm rotating. And so now it helps me see that I'll be rotating the distance from here to here is r. You're going to be seeing the way it looks as you're making this huge shell. That's really ugly. I should have saved this for the beginning, or at least the art part. I'll do my best. Here we go. We notice that when we make the shell, kind of looks like a disc, but we know there's a hole in the middle, and we know we're using shell because we are rotating our cross section parallel to the axis of rotation. Also gives us a heads up just about our viewpoint is that our height is a vertical distance. Our radius is a horizontal distance. So that's kind of nice to play with. And then just so that you see what you're actually making when you make the curve, I created a solid for you just so that you could see what we're looking at. And again, the radius is varying and the height is varying, which is why we're using shells in the first place. Okay, now, if we go through this, we have volume of 1 equals 2 pi RH times your thickness. And we already know the thickness is delta x. So now the next thing is just trying to understand what your R and your H are in terms of the curve and X values and Y values. So I'm just going to color code them based on what I labeled them on the picture. So let's kind of go back and think. Our radius is the horizontal distance. And the issue is that it's far off from our axis, our x-axis or our y-axis. So we have to be very, very careful. This is when our axis is not one of the original coordinates on the x-axis or y-axis. We have to play around with the fact that we will be using x values. We know that already. But it's always talking about whether you're taking the right or the left or the top minus bottom. So again, if we're looking at these distances, if I can, I'll try to make an ordered pair just so that we can see it. We have a point, x, y, and we have another point at 1, y. So the y values are the same. If you want to find that distance, you're subtracting the x values. So we're looking at the concept of, oh yeah, that is right minus left. So the larger curve, larger value minus the smaller value. So the right x value minus the left x value. In our case, the right x value is x. And then we're subtracting off the left x value, which is, it's not a 1, excuse me, it is a -1. Should be very careful. So what do we get? X plus 1. So that radius should now change into x plus 1. We got that down. Now height. Look at this one more time. So height is a vertical distance. So if we're kind of playing with the height along the way, the height's varying according to the curve. So we're pretty good that the height is going to use y value. We already knew that. But then we just look at, well, what curve are related to? The height is y, and the y value is the 2x squared minus x cubed. So 2x squared minus x cubed. We now have everything in terms of x. A little nicer. So with shells, it's really nice to try to understand, am I dealing with x values or y values? And how do I rewrite it so everything's in terms of what my delta will be, my delta x in this case. So we're going to clean this up just a little bit. Although if you are using a TI, a FOIL won't be too horrible with the calculator, but might as well. So let's clean this up. We can do x times 2x squared gives us 2x cubed. X times x cubed gives you minus x to the fourth. X times, 2x squared times 1 is 2x squared. And then 1 times negative x cubed is negative x cubed. So we're good there. Last thing, doesn't think we can really do anything else other than maybe combining the like terms. My left hand keeps betraying me. Here we go. So we should have x cubed, 2x cubed minus x cubed. That's x cubed minus x to the fourth plus 2x squared, delta x. And that's as simplified as it goes. And if we were trying to do it by hand, that would be what we would get into. You'll kind of experiment on your TI, I'm sure. So finally, the volume of the solid. We're taking the integral of that expression we just developed with respect to x. And that also justifies that we're using 0 and 2 as our limits of integration based on our x values. So take your time. We're almost there. We have got to factor out the 2 pi. So 2 pi, and then still we've got the integral x cubed minus x to the fourth plus 2x squared with respect to x. All of that, if we want to take, you want to take the TI one last time? Feel free to do it by hand, but I think it's just a little more tiresome. That's going to give us finally 44 over 15. Nice little exact fraction. Still multiplying that by 2 pi. We should finally get 88 pi over 15 cubic units. And now we are set. Beautiful. So my friends, the key to this section is really just patience and trying to draw things out and making sure you're mapping your radius and height to the particular x values and y values according to the functions. If you practice, you should be okay, and I have full confidence that you'll be set for your Calc 2 and your Calc 3. So thanks for listening. I will see you next class.